Okay, today in this video we are going to talk about something called the law of sines, and in the next video we'll talk about the law of cosines. And so let's say for a moment we have a right triangle. Actually, it's not a right triangle. Let's say we have a triangle that is not a right triangle. It's probably not a very good looking triangle, but you get the point. And we'll call this triangle A, B, and C. And it will have sides little c, little b, and little a. And we'll call this h, the height of that triangle. So let's say we have this triangle. Let's break it up into two right triangles. And let's use our knowledge of trigonometry, our SOHCAHTOA, and let's form some relationships. And so looking at this first triangle, we'll call this triangle 1, and we'll call this triangle 2. Looking at triangle 1, we could say that the sine of angle A is equal to the opposite side, which is H, over the hypotenuse, which is C. All right, and now we will focus on triangle 2. So triangle 2, so now we're looking at this one right here. And we will say that the sine of angle C is equal to the opposite of C, which is H, over the hypotenuse, which is A. All right, so now I'm going to solve this first equation for H. And so I'm going to multiply both sides by C. That C cancels. And I have C sine of A equals H. And I'm going to do the same thing over here. I'm going to multiply by A on both sides and get that canceled. And so I have A sine of C equals H. Now, both of these equations equal H. And so therefore, I can use substitution and set them equal to each other. If C sine of A equals H and A sine of C equals H, well, therefore, C sine of A, and this is little c, equals little a sine of capital C. And then if I divide by little c, and I divide this side by little a, this cancels, and now I have a relationship. Sine of capital A over little a is equal to the sine of capital C over little c. And by the way, that also equals sine of capital B, the angle B, over little b. This is called the law of sines. And basically, this law, along with the law of cosines, allows us to be able to solve triangles that are not right triangles. Let me repeat that. The law of sines and the law of cosines allow us to solve triangles that are not right triangles. Okay, we know that we can only use these relationships, SOHCAHTOA, on triangles that are right triangles. But if they're not, we still want to be able to solve them. And what I mean by solve is you need to know what the three sides are and what the three angles are. So when you're asked to solve a triangle, that's what we need to find. And the law of sines and the law of cosines will enable us to do that. Now let's talk about what type of triangles are we able to use the law of sines with. Well, the first type is an angle-angle side triangle. And so when we mean by angle-angle side or angle-side angle, it's pretty basic. It just simply means if you are going around this triangle, let's say you're going around clockwise, it is the order in which you have certain information. So let's say this is angle A, and this is angle B, and this is side A. So what do we have? We have an angle, nothing here, another angle, and then a side. So if we have that situation, we are able to use the law of sines to figure out what some of this unknown stuff is. So let's call this angle C or whatnot. So let's say we can use the law of sines. We would say sine of angle A over side A is equal to the sine of angle B over little b, and little b would be this unknown side right here, and that would be the unknown side. So we have enough information in order to find little b. All right, so the next type of triangle that we're able to use law of sines with is an angle side angle. So let's say we have angle A, and let's say we have side C, and we have angle B. All right, and we don't know angle C. So we have an angle, a side, and an angle. So let's see what we can do. We can say sine of A over side A is equal to, now you're thinking, wait a second, we only have two angles, A and B. We don't have angle C. But we can remember that anytime you have two angles of a triangle, you can always get the third angle because all three angles have to add up to 180. So if we have two angles of a triangle, by default, we have the third one. So now we can say sine of C over C. And now we're able to basically find any information in that particular triangle. All right, so let's say side-side angle. So let's say we have this side. We'll call that side A. And then we don't have the angle. The next thing we have is another side B. And we have this angle, capital A. So we can say sine of A over A is equal to sine of angle B, which maybe I'll put in this color. That's what we don't know. So we'll say sine of B over little b. And so we can use inverse trig in order to figure out what angle B is by taking the inverse sine. Now, let's talk about one of the triangles that you cannot use the law of sines with. And so let's say we have a triangle that looks like this, and it is we'll call this a side angle side triangle. So let's say we have this side, let's say this is 8, this is 10, and let's say this is 25 degrees. We have a side, we have an angle, and then another side in that order as we're going in this direction. Let's just see what we would get. Well, let's say we did sine of 25 over, well, we'll call that side A, we don't know that, is equal to, look, we're in trouble. We don't know angle B, we don't know angle C, so now we have two unknowns and we can't use law of sines. So you use law of sines on angle, angle, side, angle, and side, side, angle. All right, example 1. Let's say we are given a triangle that we have two angles and a side. And so here we have, if we're going counterclockwise, we have an angle. So let me circle that. We have an angle. The next thing that we have provided for us is another angle. And then as we're going around, we have a side. So this fits into the law of sines. And so it says we want to solve this triangle, which means we want to get all three angles and all three sides. So we can get angle C pretty quickly by adding 36 and 48 together and subtracting that from 180. So angle C is simply going to be 96 degrees. Okay? And so now we can use law of sines. So let me put that in there. So this is going to be 96 degrees. So now we're able to use law of sines for finding side B and side C. Keep in mind, please do not use Pythagorean theorem or SOHCAHTOA because this is not a right triangle. So throw that completely out of your mind because these are not right triangles. So we're going to get started. Sine of 36 degrees over 8. So it's the sine of the angle over the side across from the angle is equal to the sine of 48 over little b. So we're going to cross multiply. All right, so let me circle. You're going to cross multiply. Going back to grade school here. All right, so we're going to get b sine of 36 degrees is equal to 8 sine of 48 degrees. And then we want to divide by sine of 36 degrees, both sides. And so B is going to equal, well, should I say approximately, is going to be 10.115. 10.115. So that's going to be side B. And so now we're going to get side C. So we are going to say sine of angle A, which is 36, once again, over 8, is equal to the sine of angle C, which we now know is 96, over side C. Cross multiply, and you will get C equals 13.536. 13.536. Make sure you work that out on your calculator and make sure you can get those answers. Let's say you are given a triangle that has two sides and an angle. And in this particular situation, with the information that they gave us, it appears as though we can draw this triangle in two different ways. And so let's say we have side A is 6 and side B is 7 and angle A is 30. So the first way we're going to draw it is we are going to draw it, and I recommend that you always put the angle that they gave you in the lower left-hand corner. So you may want to write that as a note on your notes. Put the angle that they give you. It's just easier to visualize it in the lower left-hand corner, lower left corner. All right, so we're going to put 30 degrees here, and that is angle A. And then across from A is little a, which is 6. And then we are going to put the other side here, and that's going to be side 7, and that's going to be side B, so that means this is angle B, which by default means this is angle C, and this is side C. Now, this is called the ambiguous case, and this can be very difficult to understand, so I'm going to try to explain it and take it slowly here. Let's say we have a height that is right here, and let's say one student draws the triangle this way with the side A going out to the right. Now, what would stop another student from drawing the same triangle with the same information, where you have side B is 7, you have angle A is 30, but you have, and you know what, let me erase this a little bit. Now you have this side going this way instead of going out that way like we did in the first. Now you're swinging it this way. Still, this is a length of 6, this is a length of 7, and this is an angle of 30. And both triangles are correct. Let me review that. All they give you, they don't give you a picture, they just give you these three pieces of information right here. They say side A must be 6, side B must be 7, and angle A must be 30 degrees. So, in this first triangle, we'll call this triangle number 1. We'll call this triangle number 2. In triangle 1, ask yourself this question. Is angle A 30? Yes. Is side A 6? Yes. Is side B 7? Yes. And we drew it with the side A going out to the right, which is creating an acute triangle in a sense. All three of these angles are probably acute. Now, over here, we have angle A is 30 still. We have the side across from A, which is side A, 6, and we have side B is 7. Both triangles are correct. In this situation, you must solve both of the triangles. This is called the ambiguous case. And so we are going to have to solve them both. Now, there's ways to make this a little bit easier, okay? Now, you may say, how do I know when I'm going to have the ambiguous case? Well, it is when the side across from the angle that is given to you is smaller than the side that you do not have the angle. If this side is smaller, then I want you to visualize you can draw it in the other direction. It can swing to the right, it can swing to the left, and if it swings to the right, it's going to create triangle 1. If it swings to the left, it's going to create triangle 2. All right, so for now, we're going to work on solving triangle 1. So we will say sine of 30 over 6 is equal to sine of angle B over 7. Okay, we're going to cross multiply. So if we cross multiply, we get 7 sine of 30 is equal to 6 sine of B. And we can divide by 6. And we can take the inverse sine of both sides. So let me go ahead and do that. Divide by 6, divide by 6. And so we end up getting sine of B is equal to 7 sine of 30 over 6. Our calculator is going to give us some sort of decimal answer for that. And in order to find angle B, we will take the inverse sine of both sides. So we will get angle B to come out to be 35.7 degrees. So we'll put that angle in. And then we add 30 and 35.7 together. And we subtract that from 180 to get angle C. And angle C is going to come out to be, it's like 114.3. 114.3. So this is actually a obtuse triangle here. So I spoke incorrectly earlier. This is an obtuse triangle because it has an obtuse angle. And so now all we're missing is side C. So let me erase some of this. So in order to get side C, we're just going to use our law of sines. And it says sine of A, which we know is 30 over 6, equals sine of 114.3 degrees over side C. Cross multiply and go through the process, and C is going to be 10.9. It makes sense because the biggest side should be across from the biggest angle. And so because 114.3 is the biggest angle, then the side across from that is going to be the biggest side. Okay, so now we're in triangle 2, and there is a little shortcut that we can use here. So I want you to pay attention to, for just a moment, that if we take this side of 6, and let's say we swing it inside, okay, that means this side is 6. And this side is also 6. So that means the angles across from these sides are going to be equal because it's an isosceles triangle. So that means that if this angle B is 35.7, that means that this is also 35.7 because this side is 6 swinging to the left. This side is 6 swinging to the right, so the angles across for them should be the same. Now, notice that this forms a line, so that means this angle right here should be 180 minus 35.7 because they are supplementary angles. So if we write in angle B, we now know that angle B is simply going to be 144.3 degrees. Once again, because in this second triangle, angle B is always going to be the supplement to angle B in the first triangle. So you're going to have to do both triangles. So if we add up 30 and 144.3 and subtract it from 180, that means that this angle, which will be angle C, that will be 5.7 degrees. And you can do law of sines here. Now we'll say sine of 5.7 degrees over little c is equal to the sine of 30 over 6. Cross multiply, and little c is going to be a very small side. It's going to be 1.2. And I have not drawn this to scale. It really should look something like this, with side going in there, the angle side C coming in there like that, actually side A. And so that would make this side much smaller than the drawing, but you guys got the idea. All right, so when you have an ambiguous case, that means you have to solve both triangles. So now we're going to go back to example 2, and we are going to, hopefully this will make a little bit more sense now. It gives us the angle A is 26.3, gives us side A is 7, and side B is 6. And it asks us this question, why must this triangle be unique? And what they're asking here is, why must why must there be only one way to draw this triangle? So we are going to draw this triangle, and once again, we are going to put the angle that they gave us in the lower left-hand corner. So that's going to be 26.3 there. And across from angle A, so we'll call that angle A, across from angle A will be little a, which is 7. And then we will put angle B here, and across from angle B will be 6. Now, if we draw a height right here, it is pretty clear that this side, we cannot draw that same side with a length of 7 inside here. So in other words, we can't draw this triangle down there like that, that side. We can't draw that because it'll go past the bottom. And so there's only one way to draw this triangle with this information, because we can't take this longer side of 7 and swing it out to the right and swing it out to the left. So when the side across from the angle is bigger than the side that you are not provided the angle for, then that's going to be a unique triangle. There will only be one way for you to draw that particular triangle. So it says here we want to solve this triangle. So we're going to say sine of 26.3 over 7 equals sine of B over 6. Cross multiply, you can go do this on your own time. Cross multiply, and you're going to end up taking the inverse sine of both sides, and you're going to end up getting angle B is 22.3 degrees. And so if we take 22.3 degrees and add it to 26.3 degrees and subtract that from 180, then we will get angle C to be 131.4 degrees. And then if we have that, then we can use the law of sines to find side C. So we will say, once again, sine of 26.3 degrees over 7 is equal to, now we know angle C, so we can do sine of 131.4 over little c. Cross multiply, and we will get C is approximately 11.9. And so now we have all three sides, all three angles, and we have solved this triangle. All right, in this next example, we have a real-life application as to how we can use the law of sines to solve application problems. So it says, Forest Ranger Chris Johnson at Ranger Station A sights a fire in the direction of 32 degrees east of north. So let's talk a little bit about what that degree measurement is. East of north means start from the north and rotate east. So let's say this is Fire Station A. And this is north. Oops, that's not a good line. Let's make it a little bit more. There we go. This is north. That means he is spotting a fire that is 32 degrees east of north. So he sees a fire, and here is the fire. Don't laugh at my drawing, but there's the fire. All right, and so we'll call that north. And Ranger Rick Thorpe at Ranger Station B, which is 10 miles east of A. So here is Ranger Chris Johnson, and 10 miles down the road is Rick Thorpe. And so we know that these guys are 10 miles apart. He too is measuring where he sees the fire from the north. And he sees the same fire 48 degrees west of north. So therefore, he sees it west. So let's review our direction. That's west. That is east. So he sees it in this direction. So he sees the same fire. Now, it's important for you to label the angles correctly. That angle is 48 degrees. And this angle is 32 degrees. So we know that they form 90-degree angles because they're complementary angles. So that means by default, angle A is going to be 58 degrees, and this is going to be 42 degrees. 42 degrees. And then you can add both of those up and subtract from 180, and you'll get this to be 80 degrees. All right, so now it's a pretty simple problem. We can use law of sines to figure out how far each ranger is from the fire. So we'll start out and we will say sine of 80 over 10 is equal to, so we're looking at this angle and this side, is equal to sine of 58 over little a. Cross multiply, and little a will come out to be approximately 8.6. And then we'll do the same thing. We'll do sine of 80 over 10 is equal to the sine of 42 over little b. And we cross multiply, and we'll get little b to be 6.8. And that is the distance each ranger is from the fire. Okay, in this last example, we have a road that is sloping 10 degrees above the horizontal, and a vertical telephone pole stands beside the road. So the picture is somewhat hard to understand here. Let's say this is our pole, and let's say it was a level ground. This would be what it would look like, and so it would be a right triangle, so this would be a no-brainer to figure out what the height of the pole is. We could just use SOHCAHTOA, and we would get the height of the pole. But instead, what we have here is we still have a vertical pole, but we have, oh, that looks ugly. Let's do that again. Still have a vertical pole, but instead of a road that is horizontal, we have a road that has a slight slope to it. And so it's going to be 90 degrees. So here we have this angle that they give us is 62 degrees. So if you can imagine this line, instead of it being straight, it is 10 degrees down. That means that this angle is no longer going to be 62. It's going to be 52. All right, so that's going to be 52, and that means that this angle is going to be 52 here, right? Because these two angles are corresponding angles. All right, they're corresponding angles from geometry. So if this is 52 here, then this is going to be 52 when it's slanted. And then, of course, this is no longer 90. Okay, this was 90, but it's going to be 10 degrees more, so that's going to be 100 degrees. And so by default, 152 subtracted from 180 is going to make that 28 degrees. And so now we have all three of our angles, and the pole, it casts a shadow of 14.5 feet downhill. So that is the shadow. So now we have an angle, side, angle, triangle, and we can use law of sines. So we are looking for the height of the pole, and so we will say, we'll call this A, we'll call this B, we'll call this C. So we'll say sine of A, which is 52, over H is equal to sine of 28 over 14.5. We cross multiply and we get a height that is approximately 24.3 feet. And that would be the height of the telephone pole.